Hello, welcome back to yet another episode of CSC 263 Database Management Systems at Adelphi University. In the previous video, I explained what the relational model is all about. I basically said we have relations that consist of a collection of named attributes that are defined on a domain. The actual values are called tuples, and that the values in each tuple matches the attribute in the relation. I mentioned that these relations have a bunch of integrity constraints associated with them. Domain integrity, entity integrity, referential integrity, and general constraints. All of that stands and continues to be true. Let's dig today a little bit in the formal underpinnings of that relational model. We're not going to dig very deep. You don't need an advanced math degree to understand what I'm talking about here. It is covered in the book at section 5.1 called the Relational Algebra. We will need this because understanding what the relational algebra is and how it works will help us formulate queries and translate those to SQL at a later point. So what we're going to be doing is figuring out a question that we want to ask our database, formulate that question in natural text, English in this particular case. We're going to then translate that English text to a formal formula that is using the relational algebra. And once we have that formula, and maybe optimize that formula, we're going to use it to craft a SQL query. But between those three, the natural language description, the formula, and the SQL statements that we talk about at a later point, we will have to be able to go from each to each and translate them. For now though, let's start with section 5.1 in the book. So again, a very quick summary of what the relation is. A relation has a name. So if I'm starting to store information, for example, about people, I might call my relation people. In the database, in the relation, I should say, I'm going to name attributes. First name, last name, date of birth, email address, etc. So each of those attributes is part of a relation. Each of those attributes has a name, and it's a unique name to that relation, and it has a domain in which it is defined. For now, we'll take a little quick step ahead towards normalization down the road, but we're also going to say that the values in those attributes has to be atomic, which means I can't break them up any further. The value of an attribute, so the entries in the tuples, are all based on the same domain for a given attribute. Each tuple is distinct and there are no duplicates. So I cannot record the same exact fact twice in my database. Also important to realize is that it makes no sense in a relational database to talk about, say, the second relation, or the fourth attribute, or the sixth tuple. All of those are unsorted. And for those of you who had a little bit of a mathematical background, and hopefully also those of you who have taken our class CSC 156 discrete structures, or maybe data structures, will recognize that if I'm talking about an unsorted or maybe even unsortable collection of unique values, what I'm talking about is a set. And so we can represent a relation with a mathematical set. And that's what the relational algebra is based on. It is a theoretical language. It's not a language that we can code in or that we can speak in. It is a notational language that we use to capture knowledge. And so in that, you could say that it is a model as well. It is interesting because expressions in that language follow the closure property, which means that if I evaluate one valid statement in the relational algebra, that becomes itself a statement or an operand to another operator. Very similar to what you see in mathematics. If I put something between parentheses and I compute its value, I can replace that sub-expression with that value I have just created. That's called closure. And that is a very useful property because now I can take formulas and create more complex formulas by putting simple ones together. So that different level of abstraction again. Couple of things that are basic terminology. If I have an operator, so a thing that makes changes to data, that only takes one argument, that's called a unary operation. And in this case we use projection and selection, we'll talk about this in a second, as the unary operators. If I take in two arguments, that's called a binary operation. And in this case it's union, intersection, difference, Cartesian product, and some of the other ones. But so those are the ones that we'll talk about. Let's say that I have a database that has 100,000 records in there, 100,000 tuples about people. And for each of those people, I might record, say, 15 different attributes. Like I said, first name, last name, middle initial, date of birth, email address, street address at home, street address on campus, your telephone number, and a secondary email address and an Adelphi ID number. That's 10. And that's great that I have all that information. But at the same time, I might be trying to answer a question that really only needs an email address. And so for me then to have to worry about all 10 of those attributes as I start reasoning about this data and maybe carrying it forward to do further operations on is inefficient. And I want to get rid of all the attributes that I do not need. And that's called projection. A projection works on a single relation. And basically it creates what's called a vertical subset, but you can think of it as filtering out a number of the attributes. Again, let's take an example like behind me. Let's say that I have this relation for my temperature readings again. It contains a station, a timestamp, and a temperature. The timestamp is done in a date format that has a time zone associated with it, and the temperature is measured in degrees Celsius. I have two tuples in there, so two readings, Garden City, New York, the first timestamp and 26.0 degrees Celsius, and I have New York JFK, also New York, another timestamp. No, actually this is the same time, no, it's not the same timestamp, it's a different one, 6 hours time difference, and 25.3 degrees Celsius. If I want to only care about the temperature and the station, I can take my entire tuple and say, show me only the station and the temperature. So I'm projecting only the station name and the temperature of the relation called temperature readings, or R, and I'm creating that as an output. And so if I do that here, I use the pi symbol for projection. As a subscript, I tell it what two columns I'm interested in, but that could be any number of columns as long as they're valid. And then between parentheses I put the name of the relation or the relation itself. It could be a relation yielding from a different operation as well. And so at that point I'm going to eliminate in practice what am I eliminating? The timestamp from my readings. And so at this point I'm basically saying take my entire database and remove all the timestamps. In other words, I don't have a remove column operator, but I do have a projection operator. This does not change the database. It creates a new temporal relation with these values in it. So the database itself remains unchanged. This is just the answer to my evaluation. Once I've done the projection, I can go the other way. I can, instead of going vertical, where I eliminate some of my columns, I can go horizontal. And I say I'm only interested in rows or tuples that meet specific criteria. That's called a selection. And so, for example, if I'm looking for only those temperature readings with a temperature of less than 26 degrees Celsius, I might write the little sigma for selection, and then as a subscript the condition that I'm interested in. So temperature less than 26. And then between parentheses again, the relation or the name of the relation that I'm interested in. And that's going to yield the entire width of my relation, all of the attributes, because I'm not filtering anything vertically, I'm only filtering horizontally, that meet my criteria. Now I can of course combine these two. I can put them together by saying, let's look at this formula, project the station name. So basically only tell me the station name of what? Well, of all of the temperature readings where the temperature was greater than or equal to 26. So first I do the stuff between the parentheses, which in this case is get me all of the tuples with a temperature above 26 degrees Celsius. And then of those temperatures that are above 26, I'm only interested in seeing what their station names are. So I can combine these two operations because of that closure principles. So pi, project, station, only show me the name of the station, of what? Of the tuples that match the condition where the selection of temperature greater than 26, greater or equal than 26 from the temperature readings relation gives me the output back. And those are the only two unary operators that I have. They only take one operator in them. In addition to having these unary operators, I also have binary operators, which are operators that take two inputs and produce one output. The first one is union. What union basically does is, let's say that I have two relations. Maybe I have one relation of students and I have one relation of alumni, and I just want to put them together. I want to know everyone that I know about. Or maybe it's current students and faculty, or current students and administration. And I want to glue the output of the first relation to the end of the second relation. Or more specifically what I should say, I want to evaluate the expression that first returns all the tuples in the students relation and then returns all the tuples in the faculty relation, because I don't actually change the database by doing this. That's called a union operator. Now, I can't just glue two relations together. There have to be a couple of conditions that are met before I can do that. The first one is that if I have two relations that I want to merge together into a third relation, they must have the same degree, which means they must have the same number of attributes in them. So in other words, if I have students that have a first name, a last name, a date of birth, and an email address, so first name, last name, date of birth, and email address, with 4 tuples, then my faculty table must also have 4 tuples. Otherwise it does not fit. It doesn't know then how that would match up. Secondly, the attributes of both of those relations must be defined on the same domain. Otherwise there must be the same types. Which means that if I have, again, first name, last name, date of birth, and email address in the students, so that is first name is text, last name is text, date of birth is date, and email address is text, then my faculty table must also have text, text, date, and text. We're going to assume that when you do a union of two relations, most likely they're not only the same number and the same type, they actually represent the same type of data to make sense. But that is not something that the database knows about. The database just knows about the domain and sees, well, they're defined on the same domain, so I can treat them exactly the same. That is called union compatibility. And we have to have union compatibility before we can do many of the binary operators. So for example, I might be interested in, back to my temperature readings, all of the stations that have ever recorded a temperature below 20 degrees Celsius or above 30 degrees Celsius. I can then say, take the union, that is that large U symbol, of the selection, so only those with a temperature of less than 20 in my temperature readings table. Take my other one, which is the selection of all the temperatures more than 30 degrees Celsius in my temperature reading table, and put those together. Since I'm querying the same table twice, they are union compatible. And then from that output, I only want to see the station name. And so it's fairly straightforward to write these formulas as long as you pay a little bit of attention. If you're trying to figure out what the processing is, it might be easiest to read inside out, the same way you would evaluate the expression. If you're trying to explain to someone what's happening, maybe left to right is a better option. But you want to play with that around a little bit. The symbol for union, I said, is that large U option, the U operator, but you can also just write the word union. That's fine with me as well. So that's a union, where I just take all of the records in one relation, all of the records in the other relation. As long as they're union compatible, I'm gluing them together, and that's what my output is going to be. I might be more picky than that and say, no, I want the intersection. I want only to see those tuples that are present in both relations. So for example, I want to have, on the one hand, a query that returns all stations with a temperature over 26 degrees Celsius. And I might have a second one that returns all the stations that have an elevation of over 10,000 feet. So really what I'm asking then for is, show me all of the stations that are located at an altitude above 10,000 feet and which have recorded a temperature of 26 degrees Celsius or more. So when I start figuring that out, I have to translate that, right, into computer speak. And I have to recognize that when I'm asking that, what are all the high altitude weather stations reporting more than 26 degrees Celsius, I have to do some translations in there. And I have to recognize that that is combining two data sets. The first one is all of the temperatures, the high temperatures. The other one is all the high stations. And I'm only interested in those stations that are present in both. And that is not the U, that is the cup, the upside down thing. That is the intersection. So the intersection operator is the binary operator. It takes two relations that only returns those tuples that are present in both of the operators. And so look at the formula. The first one, project all the temperature readings with a temperature of more than 26 degrees Celsius, and from that only show me the station ID or the station name. The second one, on the bottom of the intersect symbol, well, does the same, but it only returns those stations with an elevation over 10,000 feet and has the station name in it. Notice that there are two different relations that I'm querying at this point, but because I'm condensing them down to just the station name, they become union compatible. And then I want to know which one are present in both. And now I have created a composite query, again, thanks to my closure principle, where I'm really nesting quite a bit. The first nesting is I'm nesting a select in a project. I actually do that twice. And then whatever comes out of that, I'm adding the intersection on top of. So, pretty cool that we can do this rather quickly. And again, what I'm describing here is my output. I'm not telling the computer how to go do this. I'm also only defining the declaration of what my data should look like, or what data I'm looking for that matches my criteria. The difference, basic operator, everything that is part of the first relation, but not part of the second relation. And that makes sense, because if I have a collection of, let's say on one hand, the colors of fruit, so I may have, a green apple, a green kiwi, and a green mango. On the other hand, I have paint colors, green, yellow, and blue. If I just project a color out of those, I get green and green, yellow, and blue. Subtract one from the other, and I end up with just green. Or in this particular case, I might be interested in finding the names of all temperature readings with a temperature no more than 26 degrees Celsius, which are not over 10,000 feet. So again, we're projecting the station name out of the selection of all stations with a temperature that only records values less than 26. But we're going to take away from that all the stations that are located over 10,000 feet. And so, recurring theme. There's different ways to solve the same problem. Which one to choose, that's often your own personal preference. But we can create the formula this way. The Cartesian product is a little bit more convoluted and more complicated. By itself, the Cartesian product isn't all that useful, but you can do some interesting things with it mathematically. So first of all, I take two relations, R and S, and these do not have to be union compatible. These could be any two relations. And what I'm basically going to do is each attribute in tuple R, or I should say each tuple in the first one is combined with each tuple in the second one. So for example, I see R and S. R contains three tuples. One is A1, B2, and C3. S has D4 and E5. If I compute the Cartesian product, which is the multiplication symbol, I get A1, but combined with each of the values in S. So A1, D4, A1, E5. Then I move on to B2 in R, and I do B2 with D4 and D5. Then I go on to C3, and I do C3 with D4 and E5. And so, in other words, the size of the relation returned by the Cartesian product is very large. It's the product of the cardinalities of both of the relations. So in other words, if I have a relation with 10,000 values in one, and I have 1,000 values in the second, doing the Cartesian product is going to give me a relation with 10 million records. And you can assume that that is computationally fairly intensive, and that can quickly go out of hand fairly easily. But it would give you all possible combinations. Now the thing is, we're not always interested in all possible combinations, so we want to be able to restrict this a little bit more. And that's what we call a join, where we might want to say, listen, I have, let's say, a table. Am I using an example here? Of all of those temperature readings. So it has a station, it has a temperature, and it has a timestamp. I also have a relation that has the station, again, that's a common field, the elevation, and maybe geographic coordinates, x, y, latitude, longitude. If I create the Cartesian product, I get every temperature reading combined with every possible station. Now that's not very useful under most circumstances, but what would be useful is if I then take the total set of values and reduce that down to only those where the stations match, because then what I get is an entry that says, well, in station Garden City at this time I measured 26 degrees Celsius, and by the way, Garden City is elevated at 90 feet above sea level at this latitude and this longitude. And that's the only thing that matches. And now, of course, that's useful information. If I look at this, I might see on the bottom, first I'm doing temperature readings times stations. So that creates the Cartesian product. But then I'm going to limit those rows, only select those rows where the stations match. That is called a natural join. And we have a special symbol for that. It's a butterfly symbol. And that's called an equi-join, which means that we're joining on the common attribute. And in this case, projecting out only temperature and elevation. Joins are tricky, and especially when we start talking about outer joins as well. But this is the basic concept, where we're going to take two related relations and we're going to glue them together based on common attributes. It will make more sense when we start playing with this hands-on. So the outer join comes in a couple of different flavors. A left outer join, a right outer join, or a full outer join. They're all basically the same thing, just slight variations. Again, we're taking two relations and we're merging them together on a common attribute. But in a typical join, I'm only going to include those values in my database that have a value in the common attribute on both sides. If one of the values is missing, I'm not including it. If I do want that, I have to do an outer join. And if I basically say all the values in the left relationship are always part of the output, and only those on the right will have their values combined. The rest will just be empty. That's called a left outer join. The opposite is the right outer join, and the full outer join. We don't care, they're both there. Again, a little abstract. When we play with this in the practical part, it becomes more clear. For now, remember these, look them up when you can. The most common representation of a relational database is by using a visualization based on tables. A relation is depicted as a table, just the same way that you know it from, for example, Word or a spreadsheet. A relation has a name, so it's a table with a number of columns and a number of rows. The columns represent the attributes, the rows represent the tuples. And so we'll often use a table and a relation interchangeably, or a column and an attribute interchangeably, or a row and a tuple interchangeably. Those are the same things, but the tables with their columns and their rows are just a visualization of the concept of a relation, an attribute, and a tuple. As we start working on this, what we'll find is that table names by convention are often written in all uppercase, so that it's easy to recognize. If I start drawing them out, I typically try to underline all the attributes that are part of the primary key of that relation. And if I have foreign keys between relations, I'll draw them as an arrow. So as a direction. And this is important. It's an arrow that has a meaningful direction. The source and the destination, the arrow points to the destination. In other words, if I'm going to put a student in the grading table and I want to make sure that that student actually exists, I have to create a link between the grades and the students table. The arrow goes from the grades, that's the table in which I want to ensure that the student exists, to the students that contains the definition of that student. Not the other way around. The foreign key is defined on the source, not on the destination. And so I might write it like this. I have 3 relations. Yeah, I know I couldn't count much in that slide. It will live. I have people, courses, and grades, or P, C, and G. People, I have last name, first name, email address, and date of birth. And notice that email is underlined, so email is the primary key of the P table. In the course table, I have course, credits, and department. That means that in this case, course should have been underlined, not parenthesized. And we'll fix that. Credits and department, which means that the course number is the primary key. And then the grades, the combination of email address and course is the primary key, and the grade is not. There's also a foreign key from the grades table.email to the people table.email, and that means that I cannot put a grade in the grades table for a student who does not already exist in the people table. And so now we can start thinking about this, and these are exercises we'll do in class. For example, what formulas would you write to say represent all of the names, last name and first name, of people born after September 1, 2000? Or what are the courses taken by all people with the last name of Jones? And we'll do this in class. Notice though, one thing to point out before I end this video, that in this grades table you have an email, a course, and a grade. What entity integrity said is that the primary key has to be unique. So the combination of the attributes email and course can only occur once in this database. And that means that once I have given you a grade for a course, I cannot give you a second grade without removing the first one. So if you say, me failed this databases class, so I had an F, then I cannot put a second grade in the database for me on the databases course. It cannot be done because that is a consequence of using those two as a primary key field. If I want to reflect the fact that I retook the class and now I passed, I first have to remove the grade that I got and then replace it with a different one, or update it maybe but in the end I cannot keep both facts in there. And that is a consequence of the database. If I had defined my primary key on email, then I can only get one grade, period. A second grade would not fit because email would have been unique. Or if I had defined it on course, that means that only one student could have gotten a grade for this course ever. And there would be no way to post a second grade for that course for a different student. So choosing what your primary key is has a direct impact on what kind of data you can put in your database. Okay, lots of abstract talk about formulas and operators. It is necessary to understand this and to have some hands-on with this. So we'll do this in class. We'll also do this as homework, because once you are ready to think about our relations and your operations this way, now it's going to be really easy to make the jump to SQL and learn how to program this on a computer. That's the end for this video.